Beside the Danube River in Vienna, a massive glass structure rises above the skyline, standing in stark contrast to the historic palaces and domes that have endured for centuries. This is DC Tower 1, part of the Donau City Towers complex, Austria's tallest office tower, reaching a height of 250 meters, with 60 above-ground floors. Its rippling facade makes the building appear to move under the pressure of the wind, while its slender structure must withstand powerful air currents sweeping along the Danube. How can a tower weighing hundreds of thousands of tons remain stable, operate efficiently, and transform the appearance of one of Europe's most historic capitals? In this video, join Mandarin Tech as we explore the construction journey of the Donau City Towers, a mega project that marked Vienna's transformation and reflected Austria's architectural ambition in the modern era. Designed by French architect Dominique Perrault, the Donau City Towers are a two-tower complex planned as a new symbol of the city. In the first phase, DC Tower 1 broke ground in 2010, was completed in 2014, and became Austria's tallest building at a height of 220 meters. The project serves as the centerpiece of the strategy to develop Donau City into the country's new economic and financial center. Meanwhile, DC Tower 2 is expected to reach a height of 175 meters. Although it was delayed several times following the financial crisis of 2008, construction eventually began in 2022, with completion scheduled for 2026. Unlike the original concept, which directly mirrored DC Tower 1, DC Tower 2 was revised to better accommodate apartments, a hotel, and open spaces. The combination of one completed tower and another still under construction has transformed the Donau City Towers into a decades-long story of how Vienna is expanding vertically while preserving the identity of a historic city. Before the DC-1 tower could rise into the sky, engineers had to conduct geological surveys to determine the load-bearing capacity of the ground and identify a suitable waterproofing solution for the excavation. Because the construction site was located in an area containing multiple layers of riverbank sediment and a high groundwater table, a reinforced concrete diaphragm wall was built around the foundation area. First, specialized equipment excavated deep trenches section by section. Reinforcement cages were then lowered into place, and concrete was poured to form interconnected wall panels. This structure stabilized the sides of the excavation, reduced the risk of soil collapse, and prevented groundwater from entering the construction area. Once the diaphragm wall and supporting system had been completed, excavators began removing the soil layer by layer. The excavated material was transported away from the site by dump trucks, while the depth, stability of the excavation walls, and groundwater levels were closely monitored. This process continued until the foundation pit reached its design elevation, creating sufficient space for the basement levels and the tower's main foundation slab. Next, the bottom of the excavation was leveled, cleaned, and treated to create a stable surface. There, workers installed a dense reinforcement network, with each steel bar correctly positioned, securely tied, and checked against the design drawings. Concrete was then pumped into the foundation pit almost continuously to form a unified mass and minimize weak construction joints. During curing, temperature sensors were used to monitor the heat of hydration and control the temperature difference between the core and the surface, thereby reducing the risk of cracking and ensuring the foundation's long-term durability. Once the foundation had reached sufficient strength, construction of the reinforced concrete core officially began. The tower core is the most important structural element of the building. It contains the lifts, emergency staircases, service shafts, and operational spaces. Structurally, however, it also serves as the backbone of the entire building, resisting most of the lateral loads generated by wind and helping the structure remain stable at a height of more than 200 meters. To construct the core, engineers used a climbing formwork system. After each concrete pouring cycle, the formwork was raised to a higher level, allowing the tower core to continue rising floor by floor without having to be completely dismantled and reassembled. This method shortened the construction schedule while maintaining the vertical accuracy of the structure. On each floor, the reinforcement was installed first, after which concrete was pumped upward and poured into the formwork. Surveying instruments continuously checked the vertical alignment, geometric tolerances, and position of the core against the design. For a tower as tall as DC Tower 1, even a small deviation on the lower floors could become a major problem by the time construction reached the top. With each construction cycle, the concrete core rose by another floor, gradually shaping the silhouette of DC Tower 1 on Vienna's skyline. Alongside the rising concrete core, the surrounding floor slabs, columns, and beams were constructed according to a tightly controlled cycle. First, workers erected the formwork, installed the reinforcement, and placed the concealed service pipes within the floor slabs. Concrete was then pumped upward and poured into the formwork to create each new level. Once it had reached the required strength, the formwork was removed, moved to the floor above, and the cycle began again. Around the perimeter, the columns and beams were directly connected to the floor slabs, transferring the load from each level down to the foundations, while working with the central core to increase the tower's stiffness against wind forces. As construction rose higher, delivering steel, formwork, and equipment to the correct positions became increasingly difficult. The tower cranes had to operate within confined spaces while facing constantly changing winds along the Danube. As soon as the structure of each floor became stable, installation of the exterior facade followed behind. The facade panels were prefabricated in the factory as complete modules, including the glass, aluminum frames, waterproof seals, and connection components. At the construction site, each module was lifted by crane, aligned using specialized equipment, and secured to the edge of the floor slab. The greatest challenge lay in the asymmetrical folded facade of DC Tower 1. Each module had to be positioned with the correct dimensions, angle, and location to create the visual effect of a crystalline structure in motion. After installation, the technical team continued to test the facade for water tightness, air tightness, and resistance to wind pressure. One concrete floor after another was completed. Layer by layer, glass enclosed the tower. DC Tower 1 gradually shed the appearance of a construction site and emerged on Vienna's skyline as a new architectural symbol. Once the structure and facade were completed, the building entered the stage of installing its internal technical systems. The air conditioning, ventilation, water supply and drainage, electrical, lighting, fire protection, high-speed lift, and building management systems were installed floor by floor and connected to the service shafts within the central core. At the same time, the office, hotel, commercial, and service areas were completed according to their own operational standards. At the top of the tower, the antenna was lifted by crane, aligned, and secured to the structure, completing the highest point of the building. Before handover, all systems had to undergo commissioning and inspection, from lift load testing to the fire alarm, smoke extraction, emergency power, and air conditioning systems. Only after passing these checks did DC Tower 1 officially enter operation, becoming Austria's tallest building and the first landmark of the Donau City Towers complex. If DC Tower 1 was the opening project, then DC Tower 2 is the remaining piece needed to complete the original vision of the Donau City Towers. However, the journey of the second tower did not begin immediately. According to the plan, DC Tower 2 is expected to reach a height of approximately 175 meters, making it lower than DC Tower 1 but still tall enough to form a striking pair of towers beside the Danube River. The difference in height between the two buildings is not accidental. It gives the complex a clear visual rhythm, rather than turning it into two identical blocks placed side by side. However, the project was delayed several times, particularly after the financial crisis of 2008. Changes in market conditions, ownership, and usage demand meant that DC Tower 2 no longer followed the original design of DC Tower 1 in full. Instead of serving primarily as office space, the second tower was adjusted to better accommodate apartments, a hotel, and open spaces. This also directly affected the construction process. A tower containing many apartments requires a different floor layout, different technical systems, and different requirements for lighting, balconies, and amenities compared with an office building. Construction of DC Tower 2 began in 2022 and is expected to be completed in 2026. Once the building is finished, the Donau City Towers will no longer be the story of a single tower, but a complete complex, marking the way Vienna entered the high-rise era while preserving the identity of a historic city. If DC Tower marked Vienna's leap into the high-rise era, Steinway Tower pushed super-slender architecture to the extreme in the heart of Manhattan. Located on Billionaire's Row, one of the most luxurious and expensive streets in New York, where super-tall skyscrapers stand tightly packed beside Central Park. The area has become a golden address for the world's ultra-wealthy, while also serving as a battleground for height, design, and prestige among the most ambitious real estate developments on Earth. The project was developed by JDS Development Group, Property Markets Group, and Spruce Capital Partners, with design by Shop Architects. Their ambition was to transform the tower into a new symbol of the Manhattan skyline. The development was built behind Steinway Hall, a historic building dating back to 1925 that once belonged to the piano company Steinway & Sons. Instead of demolishing the entire original structure, the architects preserved its classical Beaux-Arts facade and integrated it into the podium of the new super-tall tower. Upon completion, the building rises 435 meters with 84 floors, becoming one of the tallest residential towers in New York, while also establishing a new benchmark for the concept of super-tall slenderness in modern construction. Unlike most super-tall towers in Manhattan that combine offices, hotels, and commercial spaces, Steinway Tower was developed almost entirely as an ultra-luxury residential skyscraper for the world's billionaire elite. From the very entrance lobby, the building was designed more like a luxury hotel than a conventional residential tower. The interior uses marble, bronze, natural wood, and warm lighting systems to recreate the classic Art Deco style that defines historic New York architecture. Because the number of residents is extremely limited, the entire lobby area was designed to feel quiet, private, and almost completely separated from the chaos of Manhattan outside. Inside the tower, the residences feature high ceilings, massive floor-to-ceiling glass walls, and panoramic views overlooking Central Park and the New York skyline. Many apartments occupy entire floors, creating a sense of complete isolation hundreds of meters above the city. Steinway Tower also includes a wide range of ultra-luxury amenities, including an indoor swimming pool approximately 25 meters long, a fitness center, spa facilities, private dining rooms, resident lounges, and high-end concierge services operating continuously like those found in international five-star hotels. The emergence of Steinway Tower not only added a new icon to the Manhattan skyline, but also marked a major advancement in the engineering of ultra-slender skyscrapers. With an extreme slenderness ratio of approximately 1:24, the project demonstrated that the traditional limits of height, structural stability, and building movement could be pushed far beyond previous expectations through modern structural engineering technology. Beyond its engineering value, Steinway Tower also reflects the dramatic transformation of New York's ultra-luxury real estate market, where residences suspended high above the city are increasingly becoming global symbols of wealth and status. However, the project has also generated significant controversy, with critics arguing that it contributes to rising Manhattan property prices and alters the city's historic skyline. Even so, Steinway Tower is still widely regarded as one of the defining landmarks of the modern era of super-tall, ultra-slender skyscrapers. Vienna's DC Tower and Steinway Tower were built in two entirely different settings, yet both embody the ambition to reshape the skyline through modern engineering. Beside the Danube River, DC Tower opened a new chapter of high-rise construction for a city long associated with palaces, domes, and classical architecture. In Manhattan, Steinway Tower pushed super-slender design to the extreme, transforming a narrow plot of land into a soaring tower among a forest of skyscrapers. Two towers, two different ways of conquering height, yet both prove that bold ideas can only become icons through engineering precision. Which structure do you find more impressive? Share your thoughts below. And do not forget to subscribe to Mandarin Tech as we continue exploring the megastructures transforming our world.